University in Denmark, where he graduated in 2007. Then he did several postdocs in Helsinki, in Harvard, and also in a kind of long-term contract in Geneva in Switzerland with Markus Buttiger. And in 2015, he moved to Finland, first as an assistant professor, and by now he's associate professor. And his main topics are the electron transport in both quantum dots and also in superconductors, for counting statistics, thermodynamical aspects, and all that. And he will talk about Cooper pair splitting today. Christian, welcome again, and the stage is yours.
All right. First of all, thanks, Sigmund, for the invitation. It's a pleasure to be part of this seminar series and to have the opportunity to tell you about some of the work that we've been doing over the last few years on Cooper pair splitters. And I would, of course, have loved to visit you guys in Madrid. We can do that some other time, perhaps. And I also think that these kind of online seminars, they also have some quite nice value, and you don't have to travel, so it is quite easy and convenient. So I think it's also very good. Anyway, but let's say before going to the physics, let me start with a bit of geography, just for those who may not know exactly where Aalto University is. So up here in the left corner, you see a map here zoomed in on, say, mostly downtown Helsinki here in the red circle. And Aalto University is then out here on the left side, some 7 to 10 kilometers outside of Helsinki there. Nowadays, you easily reach the university with a metro. It takes just 10 minutes. And then you arrive here on the campus. Here's the metro station. And for me, then it's an easy walk over here to the physics department where I'm sitting right now. And the university, the name itself, I mean, it used to be Helsinki University of Technology, but then around 10 or 12 years ago, the university merged with Helsinki Business School and the Architecture School, and then it became Aalto University. And also that's from the famous Finnish architect Alvar Aalto. All right, anyway, but so in my talk today, I'll tell you about the work that we've done on Cooper pair splitting over the last 4 or 5 years.
Christian, sorry, Christian, sorry, you are not in full screen mode.
Okay, let me see. I have it on my screen. It is so now I'm a bit confused. Hold on here. Perhaps I need to press a button here and then here. Is it now?
No. Usually, yeah, it seems to, no. Click view and then there must be an option.
So I see now here in full screen, but what do you see?
The PowerPoint screen.
So is it okay or not?
It's okay, but would be more beautiful in full screen. But if not possible, then it's
okay. Yeah, okay. So I see. So do you see, like? I'm a bit confused about what you said. Display setting.
Probably. Did you share the full screen?
I'm sharing the full screen now. Let me try. Let me try again if it's not working. Hold on. Okay, let me see if this. Let's see if this now works. Is this now better?
Now it's perfect.
All right. Okay. Good. Thanks. Good. All right. Okay. Good. So let's try again here. Good. Anyway. Okay. So I'll tell you about the work we did on Cooper pair splitters, and just before getting to that, let me just say a few words about our group in general. So we call ourselves the Quantum Transport Group, and we are, as I mentioned, at the physics department, but we're also members of various quantum initiatives. So we were part of what is called Center for Quantum Engineering, which was kind of the first strategic initiative from the university to kind of start activities in quantum engineering. That was from 2015 to 2020. And then following that, we have then been part of the establishment of a Finnish Center of Excellence in Quantum Technology. So we're a group of, I think, 10 or 12 groups in the greater Helsinki area. And this is kind of a center of excellence funded by Academy of Finland, which will run until 2025. And then a few years ago, we also established something called the Finnish Quantum Institute, or Institute Q, which is also kind of it's an even bigger initiative, so far mostly focused on the greater Helsinki area. But the idea would be that in the coming years, 1 to 2 years from now, it hopefully will become a nationwide initiative. So it should collect all, say, players in this field of quantum science and quantum technology in Finland. So we're part of these different initiatives, and the group itself consists of a handful of PhD students and also some postdocs. Basically, we work on 3 topics. So we have one effort in quantum transport. That's kind of my traditional background, and here I call it dynamic quantum transport because in recent years we've gotten interested in what happens if you apply some time-dependent voltages or gate modulations to your conductor, and then if you can somehow use that to control the transport. And that's going to be the focus today. But on top of that, we have some more recent efforts in kind of a bit more in statistical physics, quantum many-body physics. We're interested in lattices with spins that interact. And then we look at different kinds of phase transitions that could be thermal or quantum or even dynamical. And some of this you perhaps can in the future, perhaps you can do it on a quantum computer. And if you like some of these lattice models, you might think about perhaps as a quantum material. So that's another interest we have. And then finally, we're interested in quantum thermodynamics. And that's, of course, when we take all these different gadgets and engines and make them very small, reach the nanoscale, and we start to have quantum effects, then of course you can ask questions about what are kind of the laws of thermodynamics once you have things like entanglement and superpositions and what have you at the quantum level there, and what's even the role of information in this context. So these are our 3 main interests, and you may of course now ask me, are there some common denominator in all of this? And I would say yes, there is. And for us, the common denominator here is really the fact that we are interested in fluctuations, so they can be quantum or thermal fluctuations at the nanoscale. So when we look at this dynamic quantum transport, here the interest is often if there's ways that we can find to control and minimize noise. For example, if you want to have a very nice regular periodic single electron emitter, then you want to minimize the noise of that current that comes out of such an emitter there. So that's really a matter of controlling and minimizing fluctuations and noise. Over here in the quantum many-body physics, we ask a bit of a different question. Here we want to learn from the fluctuation. So if we have some spin lattice where the magnetization perhaps fluctuates, or some system where the energy fluctuates, then we want to ask, what can we learn from those fluctuations? Can we say something about the phase behavior of such a system once you reach the thermodynamic limits? And then finally, on quantum thermodynamics, there perhaps the idea is rather to see if we can exploit fluctuations. So if you're doing some quantum computation on or you have some other kind of quantum device that generates unwanted heating effects, then you can ask yourself, can we take those thermal fluctuations and perhaps turn them into some useful work and do more computation? So as you see here, the common denominator in all of this is the fact that we're interested in fluctuations of various kinds. All right, and just let's say as a final advertisement, I'll just mention here that we currently do have 2 postdoc positions a bit over in this area of quantum many-body physics. We call it quantum computing for quantum materials. So if there's anyone out there who know about interested and suitable candidates, then they're certainly very welcome to apply here. I think the deadline is in about 2 weeks from now. All right, but let me now shift to the actual content of the talk today, so the outline here. So I'll start by giving you an introduction to Cooper pair splitters, and I'm sure many people here in the audience are already familiar with Cooper pair splitters, but just kind of to set the stage here so we're all on the same page, I'll give a bit of introduction to Cooper pair splitters. What are they, and what are they hopefully good for? So once I've done that, then I'll move on to some of the work that we've done. And here I'll start by discussing this topic of electron waiting times. That was kind of the first thing we did in relation to Cooper pair splitters back in 2018 or 19. So I'll explain you what that idea was about. And then I'll also, in that connection, tell you about an experiment that was done in Sweden that kind of followed up on some of these ideas that we proposed. Then after that, I'll move on to kind of the next topic, which will be what I call a dynamic Cooper pair splitter. That's some more recent work. And then we really try to think about if there's a way that we control the splitting of Cooper pairs. If you have some external gate voltage, can you use that to control when and how Cooper pairs are split? So I'll tell you about a proposal we made there, and you'll see how that works. And then following that, I'll move on to what I call the adiabatic Cooper pair splitter. And that I think and hope is an improvement of the original proposal for a dynamic Cooper pair splitter. So it's a bit different way of doing it, and I hope it has some advantages. This is still some work in progress, so I'll tell you about the idea and I'll show you some preliminary calculations, but we're not yet done with that. So this will be a bit of a first tester to see what you think about that. And then finally, if there's time for it, I'll talk a bit about entanglement detection. I mean, the idea with these Cooper pair splitters is to generate entanglement, but of course, once you do that, you also have to be able to detect it. And there we also have some ideas. And I have to say here that this I put deliberately at the end because it turns out to be a rather complicated discussion there, and I'm not sure I still have figured out a very simple way of explaining it. So I might be a bit brief here, just not to confuse you too much, but I still want to flash these ideas for how we think one might be able to detect the spin entanglement. And then after that, then I'll reach my conclusions of the talk. All right, so Cooper pair splitters. The main idea is that you want to generate spin entangled electrons. And so an example could be here of entanglement is like you have two electrons and their spins could be in a spin singlet state. And that's obviously an entangled state. And I mean, I don't need to say in this audience here how important entanglement is. I mean, nowadays it's generally believed that if we have some useful sources of entanglement, then the world will be a much better place with quantum computers and cryptography and what have you. So obviously this is kind of a resource that everyone seems to be after. And that's of course now the idea with these Cooper pair splitters, that they can generate entangled spins. And the basic idea was proposed here about 20 years ago by different groups in Switzerland, from Basel and from Zurich, that you could simply use the Cooper pairs that naturally form inside a superconductor. I mean, if we have a conventional superconductor, we know that then we have spins there. I mean, the electrons are paired up in pairs there, and their spins are in a singlet state. So we already have the entanglement inside the superconductor, and the question is now, can we get it out in a useful way there? And of course, you could hope that if you have such a superconductor, you could have Cooper pair splits so that one electron goes to the left and the other one goes to the right, but in such a way that the entanglement of their spins is preserved. And I mean, then you have this non-local entanglement that everyone wants. And then, of course, after that, it can then perhaps be evacuated further on into some, well, either further on in some circuit, or perhaps they go out here, in this case, to some normal state drains. So this is basically the idea of Cooper pair splitting. And following the proposals there from 2001, it took about 10 years, and then the first experiment came out from Schoenberger's group in Basel, and this is the structure that you see here that they used here schematically. I mean, they have a superconductor and then a nanowire across there with some gate-defined quantum dots. So that was the first experiment that was done there in 2009. And since then, there's been many other proposals, many other experiments. I won't go through all of them. I just want to at least show a few here. So the one here in the middle, that's from my next door neighbor right here at Aalto, from Pertti Hakonen's group. And the special feature about this Cooper pair splitter is that it's made in graphene. So all the dark patches that you see, that's basically graphene that has been cut out. So you see here that little black box here and the little black box here, that's two graphene quantum dots. And then the idea is you have this yellow aluminum slab, that finger going up here, which is then the superconductor that provides the split Cooper pairs. Then there's also another experiment more recent here from Lund in Sweden. There we had some collaboration with that group. So I'll come back and talk more about this experiments later in the talk. Anyway, so there's quite a bit of experimental activity, and also a lot of theory has been done. I won't try to cover all of that there. I mean, in the talk today, I'll be interested in this concept of generating entanglement, but people have also looked at other concepts, for example, thermoelectric effects. I know that Sigmund and Rafa and Robert Hussain and others have looked into thermoelectric effects in Cooper pair splitters. So that's another interesting direction. But I won't talk more about that today here. All right, but then as theoreticians, of course, we need some model, some theory we can work with in particular, and Hamiltonian, of course, is something that we like, something that captures the right physics, but hopefully is not too complicated. So one can write down some relatively simple Hamiltonian here, which is a good starting point for modeling these systems. So the Hamiltonian that we'll use in the following is given here. So this is the Hamiltonian for the two quantum dots. And there are some nice approximations one can work with, which on one hand are actually physically quite realistic, but it also turns out that in theory it helps a lot. You can make some nice approximations. So first of all, we'll work with a large Coulomb interaction on each of the quantum dots, which basically means that you cannot have more than one electron on a quantum dot. So both of them are either just empty or occupied by a single electron. And that's, of course, also convenient for Cooper pair splitting, because if one electron goes into the left quantum dot, the other one is forced to go into the other one. So that kind of enhances this splitting mechanism. So we'll work with a large Coulomb blockade U. And then it's also nice to have a large superconducting gap. If you have that, you can actually integrate out the superconductor, and then you get this effective Hamiltonian for the two quantum dots, which includes the interactions with the superconductor. And then you end up with this effective Hamiltonian where you have, on one hand, you have the two levels here, epsilon L and epsilon R, and those in experiment you can control with gate voltages, so you can move them up and down. And then we have two processes that are important. On one hand, we have elastic co-tunneling, which is a process, as you can see by the Hamiltonian here, where a single electron can tunnel via the superconductor over to the other quantum dot, so back and forth. So almost a bit like a direct tunneling process between the two dots, but via the superconductor. And then on the other hand, we have this other process down here, which is the one we're really interested in. That's the Cooper pair splitting process, where, as you can see, this process here will take the empty dot and fill in one electron in each quantum dot in this singlet state here. And both of those occur with these amplitudes here, gamma EC, so elastic co-tunneling, and gamma CPS. So that's the description of our quantum dots, taking into account the coupling to the superconductor. And now you can look a bit at the energetics here of these different states. So on one hand, you have, so here I leave out the spin degree of freedom, but let's say we have one state here, which is one electron to the left, none on the right, and that has the energy epsilon L. And we have, of course, the other situation where there's one electron on the right dot with energy epsilon R. And now these two states here, they're coupled by this elastic co-tunneling that happens with rate gamma EC. And obviously, you will have these kind of elastic co-tunneling processes if your two levels are in resonance. So if the two levels have the same energy, then that process is resonant and can occur. So we have one resonance condition for the elastic co-tunneling. That's epsilon L equal to epsilon R. But then we also have the other two levels here, or two states. We have the empty state, which has the energy 0 with respect to the chemical potential of the superconductor. And we have the doubly occupied one that has energy epsilon L plus epsilon R. And those two states here, they're now coupled by Cooper pair splitting, so gamma CPS. And there you see we have a different resonance condition, because again, this process is on resonance if the two energies are the same. And that, of course, means that epsilon L plus epsilon R should be equal to 0. Or in other words, epsilon L should be minus epsilon R. So you have different resonance conditions depending on which process you want to see and which one you want to enhance or suppress. And that's something we're going to use throughout the talk, that we can move these levels up and down and thereby control what processes can take place. Now, of course, finally, we also have to include the normal state leads, and we do that in a Lindblad master equation description. So we look at the density matrix of the double quantum dots, and then we have, of course, let's say the unitary dynamics due to the quantum dot Hamiltonian itself. But then we also have this dissipator here, which now describes how electrons are evacuated from the quantum dots and into the normal state leads. And again, here there's another nice approximation one can make if you have very large negative voltages on your drain. So imagine that these Fermi levels here are pulled down a lot. Well, then electrons can only tunnel out into the drains there. And the advantage with that is that then it becomes a Markovian master equation, which is then kind of a bit easier to treat there. So this is the last term here describes this tunneling or evacuation of the electrons into the normal state leads. So that's our theoretical workhorse. Then on top of that, we dress these Lindblad equations with counting fields. That's kind of a nice theoretical trick. And that basically allows us just to look at all kinds of statistical questions about, when do electrons tunnel out, how many tunnel out, how are they correlated, and so on. So it's a really powerful scheme that we use here to do the calculations in the following. All right, but now we can calculate different things, and typically in measurements, people have measured the current or the low frequency noise in these systems. So we can also calculate those. And here I just show you examples of the average electrical current that runs through the system here as a function of these two level positions, epsilon L and epsilon R. And basically what you see here is that indeed along this anti-diagonal where epsilon L is equal to minus epsilon R, or rather the sum is equal to 0, exactly on this anti-diagonal here, you see that we have a clear peak in the current, and that's exactly when we have this Cooper pair splitting on resonance. You also see a cross section here. You see there's a nice resonance here when the two levels are oppositely detuned there, right? So then we see that we have Cooper pair splitting, and we get that peak there exactly on that resonance there. So this is the Cooper pair splitting that we see here is being activated. And I was kind of quite happy because at the end of last year, there was an experiment coming out from Delft where they indeed looked at these kind of Cooper pair splitters again with some superconductor here and two quantum dots. And indeed in their measurements here of the electrical current, you indeed see that they have that kind of resonance there along this anti-diagonal. So hopefully our models there have some connection there with experiments. Good. All right, but okay, I hope this set the stage for Cooper pair splitting, and I'll now move on to some of the work that we have been doing, and I'll start with this concept of electron waiting times that we've been looking at. So this is a work that we started in 2018, 2017, 2018, and that's how we kind of got into this business of Cooper pair splitters. And basically the idea with this first paper was that we kind of wanted to look at Cooper pair splitters from a different perspective. So rather than looking at average current or noise, we sort of wanted to look into them in a different way. And what we imagined here, which perhaps at that time was a bit science fiction, we simply thought, okay, what now if you actually would have some detectors here related to your drain electrodes here? If you've had some detector that somehow could say click every time an electron tunnels out into either the left or the right lead here, what could we learn from that if we had some real-time detectors of the tunneling events? So we looked into that, and our suggestion was to look at what we call the waiting time and how the waiting time is distributed. And so the waiting time is the time between clicks in your detector. So imagine that your left detector here says click every time an electron comes out here. Now you can ask the question, given that I get a click now, how long time will pass until I get the next click? So it's the time between subsequent clicks. And obviously, since this is a stochastic process, it won't be a fixed time. It will fluctuate and will have some distribution, and that's what we call the waiting time distribution. And if you look at the distribution of waiting times that we calculated between subsequent clicks in the same lead, so the left lead, for example, we get a somewhat perhaps a bit boring result. We basically see that you have a very strong suppression of the waiting time at short times. Basically, you never find a waiting time which is 0. That's simply just a consequence of the fact that we have this strong Coulomb blockade. So when one electron comes into the quantum dot and tunnels out, it says click the detector, but now the quantum dot has to be refilled until the next electron can tunnel out. And this refilling, or this kind of blockade phenomenon here, that simply means that we cannot have a waiting time which is 0. So there's a strong suppression at short times, and then it levels off, and then there's a long, perhaps longer exponential decay here. But in some sense, a bit undramatic here. But now we looked, on the other hand, at what we call the cross waiting time, and there we look at the time between clicks in different detectors. So if it says click in the left and clack in the right, then we say, well, given you get a click now, how long time do I have to wait until there's a clack, right? Or the other detector says something. And here you get quite a different impression, because you see here at short times, you have a very strong enhancement of this cross waiting time there. And that's, of course, exactly the signature you would expect if you have Cooper pair splitting, right? Because then a Cooper pair is split, one goes to left, and quickly right after the other one will go to the right. So the fact that we have this very enhanced waiting time at short times, that is exactly the signature you would expect for Cooper pair splitting. So by looking at these cross waiting time distribution, you really see strong signatures of Cooper pair splitting. So that's the peak here at short times, and then there's a longer exponential decay here, which is then related to the waiting time between subsequent Cooper pairs. So anyway, so the idea would be to look at these waiting times and analyze either the time between clicks in the same detector or in between opposite detectors, and from that you would learn about Cooper pair splitting. So that's kind of the main idea of that paper. We also calculated other things, but I think this is the kind of the upshot of our idea. So of course you can do such a calculation as a theoretician here, but then after that there's not much you can do more. You just have to wait, and hopefully someone will pick up on the idea and hopefully try to do the experiment. And actually that happens. So just a few years later, we were contacted by Wilhelm group in Lund, and he contacted us and said, well, we're actually going to do what you've been thinking about there. So they have a setup here, again, a Cooper pair splitter. It's of course a bit different than what we suggested. That's often how it is with the experimentalists. You suggest one thing and they do something a bit different, and then you have to go back and think a bit about that. So what they did here in this case is, again, they have a superconductor here in blue. And now in this case here, it's not coupled to quantum dots, but rather to two metallic islands. We have a left and a right island there. And then also in this case here, there's no normal state drains. So it's not like you have a transport setup, right? You just have a superconductor, and then it's coupled to these two islands. So electrons can tunnel in and out between the superconductor and the islands. And now on top of that, they had two charge detectors here to the left and to the right. So basically what you do here is you have a current running through this left detector. And the main point is that the conductance of that detector here is very sensitive to the presence of electrons on the island. So there's some capacitive coupling between the island and the detector. So in other words, every time an electron tunnels into the left island, you'll immediately see a suppression of the current running through the detector here into the left. And similarly here over on the right-hand side, when an electron tunnels into the right island, you see a suppression of the current in the detector here to the right. Now you simply measure these detector currents in real time. That's what you see here to the right. And you can see that both of them go between two levels, corresponding to having, say, 0 or 1 extra electron on each of the islands. And now by analyzing these time traces, we can, of course, deduce what kind of processes are happening in the Cooper pair splitter. So if we start by looking at this first point here that I call 1, well, we see what happens here is that nothing happens in the right detector. The current stays the same, but you see that in the left detector, the current goes from a low value to a high value, which means that an electron must have tunneled from the left island into the superconductor. So it would be this kind of sequential tunneling event, which sometimes happens, when the electron gets excited over the superconducting gap. So you have these single electron events. That's what we then see here at 1. And of course, you can continue further down the timeline here. And here too, something more interesting happens, because now you see that simultaneously you have a suppression of the current in both detectors. And that, of course, means that at the same time, electron has tunneled to the left and to the right. So that exactly would be what we would expect from Cooper pair splitting here, that you simultaneously have tunneling into the left and to the right. And of course, then one can continue further down here, and you see that you have other kinds of tunneling events. Electron tunnels in, or perhaps you have this elastic co-tunneling when an electron goes via the superconductor from left to the right. And now they measured for a long time, so you can do a lot of statistics. You can count millions of tunneling events, and then one can analyze that. And indeed, that's what we'll do in the following. And of course, one thing one could ask, if you want to be a bit critical, you can say, well, here we have two simultaneous tunneling events happening, but is it really Cooper pair splitting, or could it just be two uncorrelated or unrelated single tunneling events that just happen at the same time, right? That would be another option. So strictly speaking, we don't know that this for sure is Cooper pair splitting. So to really answer that question, we have to look a bit more at the statistics and analyze that in more detail. So what we did was we looked at different correlation functions, where we analyzed the G2 correlation functions, and G2 correlation functions are somewhat similar to waiting times, but not quite the same, because when we look at a G2 function, we ask the question that if I get a click now, what is the probability that I'll get a click later on at a later time? But in between there, you could have had other detections, right? So waiting times really talk about subsequent events, whereas the G2 functions, they just ask, okay, if I have a click now, what's the probability to have a click at a later time? And in between there could have been a detection event. So it's a bit different quality. They're also a bit easier to measure because they're less dependent on the detector efficiency. I mean, with a waiting time distribution, you really have to be able to detect every single event, and that's not necessary for a G2 function. Anyway, so again, we looked at the G2 functions, and we looked again, one hand on the autocorrelation G2 functions. So that would be clicks in the same detector. And again, here we see we have a strong dip at 0 time delay, and that's again due to this Coulomb blockade, that we cannot have two electrons tunneling into the island at the same time. So you have a strong suppression there, a dip in the G2 function, which is, I mean, again, just this kind of signature that we have single electron tunneling. On the other hand, if we look at the cross G2 functions where we look at clicks in the different detectors, we get a very different picture here. You see you have a very large enhancement of this cross G2 function. You see it has values around 200. The autocorrelation one is on the order of 1, right? And 1 would be kind of uncorrelated events, right? So you have a very strong enhancement of the G2 cross correlation function, and you also see the time scales are very different. You have a dip here which is kind of on a second scale, and over here which on a millisecond scale. So it's really a very narrow peak, and that is exactly the signature that we really have correlated events when they happen at the same time, right? If these kind of events that look like Cooper pair splitting, if they were just random single particle events, the value of the G2 function would be 1, but we see this very large enhancement here. And by analyzing the height of the G2 function here and the area, we can actually say that with more than 99% fidelity, when we see these two events happening at the same time, it's with more than 99% fidelity, the splitting of a Cooper pair. Doesn't rule out they could be single electron events, but with very high probability they are indeed, it is indeed Cooper pair splitting. All right, so then we went a bit further and we also analyzed these waiting time distributions that we had originally proposed there, and we see things that fall quite well in line with what we had predicted, namely again for the waiting time distribution for tunneling into the same island, there we see this strong suppression at short times, and then it kind of levels off exponentially at longer times. And again, if we look at the cross waiting time distribution, we have this very large enhancement here, which is the signature of Cooper pair splitting, and again with a tail here that then tells you about the time between subsequent Cooper pair splittings. All right, so this was 2021, so 2 years ago, and here I'd like to mention that in parallel with this experiment, there was another experiment or collaboration we had with Rolf Haug's group in Hanover, which is, well, a bit similar in spirit, but a different setup here. So in Hanover, they looked at just a single electron transistor, so just a single quantum dot, and they also measured this waiting time between the tunneling of electrons in and out of the quantum dot here. So kind of similar to the Cooper pair splitter, but just with normal state electrons here. But then what they did, by contrast, in the Hanover experiment was that they had a periodic backgate. So as electrons were tunneling in and out, they also had a backgate that they moved up and down, and thereby they were affecting the tunneling of electrons. So we had some ideas about these kind of setups there, and we collaborated with them on kind of, let's say, developing a theory for their experiment. And there's some nice, interesting discussions one can have here with, let's say, how the drive locks in with the tunneling of electrons, and whether you are in an adiabatic or a non-adiabatic regime here. I won't go much into more detail about this here, but the point I want to make here is that you can imagine this was back in 2021, and we had these two experiments. On one hand, the real-time detection of Cooper pair splitting from Lund on one hand, and then on the other hand, we had the experiment from Hanover, where they also detected electrons in real time, and here they had this drive there that they used to modulate the tunneling of electrons. And now, given those two experiments, perhaps it was not rocket science to come up with the idea that, well, why don't we take a Cooper pair splitter and then use some voltage modulations to kind of affect the tunneling and the splitting of Cooper pairs. So that's kind of what led us onto that idea. And indeed, that's what I'll talk about here in the next section here. I'll tell you about our proposal for a dynamic Cooper pair splitter, where indeed the idea is that we use a gate voltage to control the splitting of Cooper pairs. Particularly, we want to move these levels up and down in a clever way that kind of will then allow us to have Cooper pair splitting on demand. Okay, so this is the setup again here. Again, we have our superconductor. We have left and right quantum dots with those quantum dot levels inside, and then tunneling out to the normal state drains. And now the idea is that we want to use voltage, gate voltage here on one of the quantum dots to move that level up and down. And now the idea is we want to use this to kind of turn Cooper pair splitting on and off, and thereby be able to have kind of a periodic splitting of Cooper pairs. So basically, the idea is that we have this periodic voltage here. So we have a periodic signal, and we divide that period into two phases, phase 1 and phase 2, one which we call the loading phase, where we split the Cooper pair so that electrons arrive on left and right quantum dot. And then after that, we have the unloading phase coming here, where we then want to emit the electrons into the normal state drains. So how does it work? Well, okay, in the loading phase, we want to start with empty quantum dots, so nothing there. Then we want to tune the levels into that Cooper pair splitting resonance where epsilon L plus epsilon R is equal to 0. So we are on resonance. And now when we're on resonance, the system will oscillate coherently back and forth between being empty and being doubly occupied. And of course, once you have such a coherent oscillation, you can make a pi pulse where you swap from empty to doubly occupied. And you get that by being on resonance exactly for a time given by pi over 2 times the Cooper pair splitting amplitude, right? That's kind of have a coherent oscillation there, so a pi pulse. So we do that. So first tune into the resonance. Be sure that you sit for the right time there. You swap in split Cooper pair. And once we do that, we tune away. When we go into the unloading phase, we tune away from that resonance. Now Cooper pair splitting cannot happen, so you cannot go back and forth between the superconductor and the quantum dots any longer. And instead, you just sit there with filled quantum dots. And now you simply have to wait for some time, which would be 1 over, let's say, the coupling gamma here to the leads. And then if you wait such a long time, eventually those electrons will tunnel out into the left and to the right lead, and then we're back and we can restart the drive here. So this is kind of the idea with this dynamic Cooper pair split of tuning in and out of resonance, and then when we're on resonance, do this pi swap there. And of course, we have to test if it actually works, at least in theory. So of course, we can calculate various things. So here I show calculations of the average current running into one of the leads as a function, on the one hand, of the duration of the loading phase, so that's T1, and then we have 2 different curves here corresponding to the duration of the unloading phase. And of course, the key point here is that if you look at exactly that time where the loading phase takes this time pi over 2 gamma, well, then you see that we exactly reach an average current of 1 electron per period of the drive. And that's exactly, of course, you would expect that you get 1 electron into left and right per period of the drive. So you see that we really have to match the time, we have to fine tune the time here. And you also see we really have to wait, let's say, sufficiently long here. So gamma times T2 has to be, say, 5 or larger. Then we are sure that we get the electrons emitted during the unloading phase, right? So there are some sort of sweet spot conditions here where this works. And if we work on that sweet spot here with the red dot, well, then we can also see in other quantities such as the G2 functions. There again, we get a nice enhancement of this cross correlation function there that shows that, okay, we have Cooper pair splitting on, let's say, periodic Cooper pair splitting. And that becomes extra evident if you also look at the waiting time distributions again. So here on the left one, we look at the waiting time between electrons going into the left lead. And of course, if we have this nice periodic Cooper pair splitting, we expect to have 1 electron coming out, and then you wait another period and the next one comes out. And so the waiting times here should be nicely peaked around the period of the drive. And that's also what you see. Again, if we look at the cross waiting time distributions, then we also, again, we have this enhancement at very short times. That's the signature that we do have Cooper pair splitting. They come out left, right, left, right, left, right on the one hand. And we have this other peak here around the period of the drive, perhaps a bit shorter. And that's the distance between the last electron from one Cooper pair and the first electron for the next Cooper pair. So that will be a bit shorter than the period of the drive. Anyway, we see signatures there in these results that we have this kind of periodic splitting of Cooper pairs that we're after. So at least, let's say, in the theory, this proposal works. So I was kind of happy with that. On the other hand, I was also a bit skeptical on some points. In particular, what I did not like so much was the fact that in this loading phase that we work with these resonance conditions, right? So we're telling the experimentalist, please tune your levels exactly in so that they sum to 0. I mean, that's already a bit demanding. And then once you've done that, then we also ask you to stay on that resonance exactly by a time given by pi over 2 gamma, where gamma is this Cooper pair splitting amplitude. And if you plug in some realistic numbers, you're probably down somewhere in the nanosecond scale, right? So you have to, on one hand, tune them into the right resonance, and you have to stay there for 2.7 nanoseconds and then tune out again. So there are some difficult resonance conditions there. So I would kind of expect to get some raised eyebrows from the experimentalist if we would go and ask them to do that. So I kind of, let's say, I was happy that this worked in principle, but I thought, can we do a bit better than working with these resonance conditions here? So that kind of brings me to the following point here, and that is now the adiabatic Cooper pair splitter, which I hope could perhaps be a better suggestion where we can avoid some of these resonance conditions that we've been working with. And now, okay, so how should one do it, and what's the idea here? And well, basically the idea for how to do this you can get by making a rather simple drawing here. So the idea of the Cooper pair splitter came simply from making this drawing here. So I've drawn it by hand, and basically what I'm drawing here is the energies of the two interesting states, namely on one hand the empty state, well, that has energy 0, so it's just a flat line here, the flat dashed line. And then I plot the energy of the doubly occupied state. I remember that has energy epsilon, so that's also just another straight line here with that I showed with dashed. So that's our two energy levels there. And then of course on top of that we have to remember that they're coupled by the amplitude for Cooper pair splitting. So this is of course just an avoided crossing. We get a splitting here given by this gamma CPS, right? So you make such a simple drawing like that, and then suddenly it becomes much clearer what to do. And let me just remind you that in the previous proposal with the dynamic Cooper pair splitter, what we did was we started out here with the empty quantum dots. Then we tuned epsilon into 0 into that resonance. We did the pi pulse to swap up to the doubly occupied state up here, and then we tuned epsilon up again. So we would sit up here with the doubly occupied quantum dots, and then once we sit here, we just wait, because eventually the electrons will tunnel out to the drain electrodes and will bring us back down to the empty state again, right? So then we simply cycled around like that, you know, start with empty, into the resonance, do the pi pulse, up again, and eject. So that was kind of the idea with the dynamic Cooper pair splitter. But now, I mean, again, when we do this drawing here, of course, you can't help asking yourself, when we start here in the empty state and reduce epsilon, I mean, before we stopped here at epsilon equal to 0, but you can ask yourself, why don't we just continue further down and keep on reducing epsilon? Because if we do it like that, we also end up in the doubly occupied state, right? So if we do a slow adiabatic transition here, I mean, we have to be careful that we don't do it too fast, because then we get a Landauer-Zener transition, then we'll just go back to the empty state, so that won't help. But if we do it slowly enough, we can just move along this this ground state energy here, and then simply move us down into the doubly occupied state. Then we've also loaded in a Cooper pair, but without relying on any resonance condition. We just have to do it slowly. And so what do we do when we're down here? Well, okay, nature will solve that problem for us, because again, when we sit down here, we know that it's an open system. I mean, eventually the electrons will tunnel out. Once they tunnel out to the normal state drains, well, then we're up here in 0, 0, right? Then we've ejected the electrons there. So then we sit up here, and then we can ask ourselves, well, what do we do next? Well, what can we do? Well, we can almost only just increase epsilon again. So let's do that. So then we just increase epsilon, and then of course we move back here, and now along this excited energy. So then we move up here, and then again we have gone into the doubly occupied state. In other words, we have loaded in a Cooper pair again, and then we sit up here, and what happens? Well, okay, now again they will be ejected into the lead, so will bring us back to the ground state, or to the empty state again. So simply doing like this, I mean, move slowly here to avoid any non-adiabatic excitations, move down here, load in a Cooper pair, now you get ejected out here, and then we move back up again, and so forth. So that's kind of our new cycle there. And again, here in this case, we don't rely on any resonance condition. It's just adiabatic, and on top of that, you get 2 split Cooper pairs every time you cycle around in this scheme here. So that's the idea with adiabatic Cooper pair splitter. We're now trying to see if it works, and so far it looks at least promising. So I'll show you some recent results. This is pretty much straight out of the oven here, so we haven't even plotted them so nicely yet. But basically what you see here is the driving protocol when we move the levels up and down. It might look that it is a bit, you might think that this looks a bit non-adiabatic, but actually on a scale given by gamma CPS, this is actually slow enough that it's still adiabatic here. So this is our adiabatic driving protocol, and now here we calculate on one hand calculate the time-dependent current in one of the leads, and you see you get these bleeps here, bloop, 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 2 per period, and that's exactly every time we get a split Cooper pair and we emit electron to the left, we bump and bump. So each of these peaks here, that correspond exactly to this, to the splitting of Cooper pairs. Then of course, we're now analyzing this in further detail, and one thing we're doing is to calculate the average current per period as a function of the driving frequency. And so these are also very recent results. I think we can still improve a bit on it, but basically you see here the number of electrons that are emitted per period of the drive as a function of the driving frequency, and then for some different parameter values here. But again, the important point is here that if we go to low enough frequency, see here we get a nice flat plateau where we exactly get 2 electrons emitted into each drain electrode per period of the drive, and that's exactly, of course, this kind of quantized emission of electrons where we really have periodic splitting of Cooper pairs. If we start to drive it too fast, well, then we start to have these non-adiabatic excitations, so then we don't get Cooper pairs split, and eventually we go into some non-adiabatic regime here where it doesn't work so well any longer. I think actually, I mean, as I said, these are still preliminary results, and I think we could change something in our protocol and actually have this adiabatic regime extended to higher frequencies. I think we're doing something which is not so clever now, and we can improve on that, and then we can push that adiabatic regime there to higher driving frequency, which would I mean, of course, would be attractive there. Anyway, so this is basically where we are now. From this is basically this week. This is where we are, and we'll of course continue. And the obvious thing is, of course, also to calculate the low frequency noise. And of course, we expect and hope that when we are on that plateau there with regular emission, we will correspondingly also see a very low noise there. So that's the expectation, that we will see that, and that's of course it's another then signature that it's working well. All right, okay, but let's say I hope in some near future we can report more on this, but this is still work in progress. All right, okay, then I have hopefully a little bit of time here at the end to also briefly discuss this idea of how to detect the entanglement. As of course, let's say if all this works, then at some point you would like to know that you actually do create entangled spins, and that's of course, let's say the holy grail with all of this. So we've been thinking about that, and let's say the key point, of course, is that we want ways to know that the spins that come out, or the electrons, that their spins actually is entangled. And this is, let's say, not super easy, and one can approach it in different ways. And what we've been doing is we've been looking into entanglement witnesses, and basically the idea with entanglement witnesses, basically you want some operator, here we call it W, you want an operator or some observable that is designed in such a way that if you take the expectation value with respect to all separable states, then you can put an upper bound on it. You can say, well, if those, for all the separable states, the expectation value of this observable can simply never be higher than some value. And of course, together with that, you also want to have it designed in such a way that if you actually have entanglement, then you can actually violate that inequality there, right? So in other words, if you get an expectation value that exceeds this value, W max, you can say, well, that state could not have been separable. In other words, there must have been entanglement. So finding these witnesses there and actually kind of making that bound on the maximum value for all separable states, that's kind of quite an art, and not so easy here, right? So one has to really think about what would be a good observable that could function as a witness here. So we've come up with an entanglement witness here, and okay, it looks a bit complicated here, but basically an entanglement witness would consist of 3 cross-correlation measurements of the spin currents. So you imagine you have some ferromagnetic leads where you can control the polarization, then you can have different polarization angles, and what we would need in our proposal is that you can measure these spin cross-correlations with 3 different polarizations there. This has been something people have been thinking and hoping to do for a long time, to measure these spin cross correlations there. And at some point it looked like it was almost impossible. But then again, last year there was the first experiment coming out from Basel, where they actually measured these spin cross correlations in these kind of Cooper pair splitters. So perhaps there is some hope that one can do it. I'll skip more details here because it gets very, very complicated, this discussion here. I just want to show that we at least tested our witness on our model of a Cooper pair splitter, And the most important thing is here that we have a knob in our model, which is this gamma d, that's basically a defacing rate. So we can simply test, well, can we detect entanglement? I mean, can we exceed this value for separable states? Is that possible? And how can we exceed it, let's say, as a function of this defacing rate? And basically we find that, okay, if the defacing is not too strong, there is some hope that one could actually detect the entanglement. All right, okay, but this essentially brings me to the end of the talk here. So just kind of the outline is basically, or the conclusion is the same as the outline. I mean, so I told you about this general idea of Cooper pair splitters, and then we looked at the first idea for measuring electron waiting times and used that to characterize Cooper pair splitters, and you saw the experiment there from Lund. And then I talked about these more recent ideas for first a dynamic Cooper pair splitter, and then our kind of subsequent proposal that we're working on now, where we want to do it adiabatically. And then finally, at least I flashed these ideas on how one hopefully could measure the entanglement that's generated from these Cooper pair splitters. So with that, I'd like to thank you for your attention.
Okay, Christian, thanks a lot for this interesting talk. Are there questions? So everybody, there is Alfredo raising his hand. Okay. Ramon, are you taking care of it?
Yeah, hello.
Hi.
Hello, Christian. Thank you for the talk. And well, nice to meet you. I think we never coincided, but thanks for giving this talk here. And well, I'm interested. I like very much the idea of Cooper pair splitting in time resolved. No? I wonder, however, well, there are some simplifications in your description of the processes that you take into account. No? Principle, there is no possibility of poisoning, I think, in your description. Basically, you just keep these two states empty, or 1,1 or 0,0, and what about the spin also dynamics? Don't know if you have arguments to, well, not to take into account these complications.
Right. I mean, so okay, a few comments. We do include the spin, so that's there. I mean, I just didn't put them in the states there. I mean, so of course, each of the chart states, they also have some, they're also spin resolved. So that I mean, that is there. And even in those last calculations I showed, we put in some decoherence of the spin superpositions and so on. So that we can somehow handle. Then you mentioned this poisoning. That we kind of, let's say, it doesn't work to our advantage, so we kind of put that a bit away. I mean, we don't have it in the theory. Let's say we try to go for, let's say, a pretty or very simple model that hopefully kind of, let's say, is tractable. So kind of, so that's been a bit the spirit. But actually, in the experiments I showed you, I mean, there you have these kind of single electron or quasi-particle poisoning processes. They do happen, and so when we So in our original theory proposal, we didn't take them into account. But of course, when we had to actually describe the experiment, we had to take that into account and build it in, right? So we in the actual description of the experiment, we do have it.
Somehow relax the condition of infinite gap, no? Essentially.
Yeah, sure. Yeah, I mean, this one could do, right? And let's say, we work with these different assumptions there. I mean, one could also, okay, I mean, is the Coulomb interaction really so large as it is, and are the voltages as low as they are? The thing is, in that limit there with large interactions, large gap, low voltage, the appealing thing there is that the model itself becomes tractable. I mean, so then we can actually, many of the things that we can calculate analytically, and I think I know for sure, for example, if you had like a finite voltage on the least, then you get into all kinds of non-Markovian complications, which, I mean, in reality they may of course be there, but it just becomes so complicated, and that's why I like to do the simplest version there that can be solved, right? But I mean, but one can definitely, you can add more things on, and well, it will be more complicated. And of course, perhaps as you also say, it's probably also more perhaps more realistic experimentally. I mean, some of those effects will come in there. So anyway, so there's some trade-off there.
Okay. Thank you, Christian.
Michael?
Yeah, Christian, hi.
Hi, Michel.
Thank you very much for a very nice talk. I have a small question. Can we go to slide with adiabatic Cooper pair splitted and with current? Yeah, current. Next, yeah, here. I would expect in adiabatic regime current pulse to be symmetric. Is there any reason why it should be asymmetric in this setup?
Okay. Let me think. Let me think because I haven't thought about it.
Okay, fine.
No, but I
it's good. It's good answer.
Yeah, but I think. Okay, I have to think a bit more about it. But I kind of. I mean, my impression is that okay, you at some point you are allowed to decay, and then that will be an exponential decay.
No. Adiabatic,
okay.
Exponential decay, adiabatic, it's a different thing. I also want to make another remark. In one unrelated to this problem, we found that Markovian description is not consistent with the, so to say, scattering description. And scattering description is I would say this adiabatic regime here is more quantum behavior than Markovian description can provide. Maybe this is the reason, but I'm not sure.
Yeah, but maybe also I think perhaps like I mean, Misha, we know each other very well, and I think in this context here, perhaps my notion of adiabatic is a bit different from what we typically think about in Floquet scattering theory. So for me, when I talk about non-adiabatic and adiabatic here, the key question is really, I mean, when you drive across, I mean, when you move along this.
I agree.
The ground state here, you cannot. I mean, there's a speed that you cannot do it faster than a certain speed, because if you do that, you will go from empty over to empty again, right? So that is the adiabatic DCT that can break down at too high frequency. You move too fast.
I completely agree, but you know, another consequence of adiabaticity is that this gamma process can happen not necessarily so far as you draw, but also in this middle area and even before.
Yes, absolutely. I mean, that's actually. I mean, so let's say we were still working on getting this to work perfectly, and there is really. One has to be careful with these different time scales, because indeed, as you say, there's also inside this area here where we are on resonance, you can also have the capital gamma processes happening. I mean, in other words, you can start. I mean, the electrons can start to at this point here be evacuated out to the least. So there is some. You have to a bit play with the parameters and really work in the right regime to make this work. So that it's actually it gets a bit complicated. So it's totally true.
Thank you very much.
Yeah, sure.
Yeah, actually, I have one related to that. You mentioned that, say, one limit is to keep the tunings stable for a certain time.
Yeah.
So that should set somehow the limit of, say, low frequency to which you can go. When otherwise you will have kind of Landau-Zener transitions between fluctuating levels. So how much can you go down to low frequencies or to the adiabatic regime?
Yeah, okay. Now, I didn't totally hear all you said, Sigmund, but I think I heard enough. So let me try to answer what I heard. Let me see here. I mean, so you're concerned about this. How low can we go?
Yeah. How far can we go?
Yeah, and first of all, let me say that actually, say interest-wise, of course, we want to go to high frequencies as possible. I mean, let's say ideally. The further we, and I think actually we can change our protocol. We're doing something which is not totally clever. We can do something which is a bit better. So I think actually we'll be able to push this red line up by several orders of magnitude. Basically, kind of the way we're doing it now, we kind of move through the whole change that we do with the same speed. And actually, it would be much more clever to do it. You know, let's say. I mean, right now we move with the same speed along the whole line here, but actually it's much better to move fast and then slow down as we go through the crossing, and then speed up again. And I think from that we will be able to do it faster. But anyway, so there's now you're talking about the low frequency regime. And there indeed there are some problems already. And let me just think what it is. Yeah, that is okay. That is exactly that. If we do it very, very slowly, we spend too much time around the resonance, and then during that transition, we can actually have that the electrons can escape out, and there can be a new loading in and another escape, and that actually gives you a larger current, and that's exactly what you also see here. So it is a problem in that transition area. If we also start to have the electrons leak out while we're transitioning, that we have to watch out with. So yeah, I mean, so. Okay, I think we still need to think a bit about things here, perhaps improve the protocol, and I think we know how to do it there. I think we can somehow improve this. So this is, yeah, it's preliminary still, but hopefully shows the right trends.
Are there further questions? But there's one thing that I noticed in the very beginning when you showed the experimental version of the autocorrelation function, which seems to be perfectly symmetric. Is that by construction?
That is a good question.
When you process the experimental data?
Yeah, no, I can certainly tell you that. I mean, now I'm trying to think back. That's actually a good question, because it doesn't have to be symmetric. But I agree now that you say that they actually look like they are quite symmetric there. I can't remember. I would have to look back and see how that analysis actually. I mean, you're asking whether was it just a mirroring or was it actually? Yeah, I honestly I can't remember. I have to get back to you on that.
Okay, so if I see no further questions, we close the official part and go to
let me okay. Sorry, Sigmund, I'm interrupting you. Let me just say actually, because now of course I also look at the cross correlation and they are not symmetric. So I mean, yeah, somehow yeah. So I say certainly I don't think in the. I mean, I don't think these cross correlations have just been mirrored. I mean, I think it comes out of the analysis. Because I mean, we analyzed in the same way the cross correlations and the autocorrelations. So something, yeah, there's something there in that somehow make them come out symmetrically. Sorry.